Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Imagine, for just a moment, sitting inside a cramped metal cylinder.
Right, like a really, really small submarine.
Exactly. The bulkheads around you are just packed tight with avionics, life support machinery, and the recycled air has this constant mechanical drone to it. You look out a reinforced quartz window and Earth is entirely gone.
Which is a terrifying thought all on its own.
Oh, absolutely. And you've been sitting in this specific tiny geometry for over 6 months. Every single day, high-energy galactic cosmic rays are passing right through the hull, just threading through your cellular structure.
And your body's basically turning on itself at that point.
Yeah, because you are in continuous microgravity, right? So your osteoclasts, those are the cells that break down bone tissue, they're operating way faster than your osteoblasts can rebuild it.
Your bones are literally dissolving.
It's brutal. Your fluid distribution has shifted upward, increasing intracranial pressure, and it's actively altering the shape of your eyes. You are enduring this profound, basically systemic degradation of your own biology just to reach Mars.
It forces us to confront a really dark reality about human physiology. We focus so heavily on this grand vision of becoming a multi-planetary species, you know?
Right.
But the physiological toll of the commute itself is this massive barrier. The human organism is exquisitely calibrated for a 1G environment and the protective magnetosphere of Earth.
We are Earthlings through and through.
Exactly. Remove those conditions for half a year, and the body just initiates a cascade of systemic failures.
So, to understand exactly how we're going to fix this, we have to look at the radical shift NASA is aggressively pursuing. They are going after a technology that has lingered between, like, engineering reality and myth for 60 years.
Nuclear propulsion.
Yes. Splitting atoms in space. We need to understand how this technology could cut the journey to Mars to just 3 or 4 months, which would make humanity a true spacefaring species.
It's the ultimate game changer.
But to understand why we are taking this massive nuclear leap, we first have to understand the fundamental flaw in how we currently get to space.
Right, the old school methods.
Yeah, every single spacecraft leaves Earth by burning chemical fuel. Rockets mix fuel with an oxidizer, they ignite it, and they blast expanding gas through a nozzle. Newton's third law, right? Gas pushes down, rocket goes up.
Simple physics.
Okay, let's unpack this. Chemical propulsion is basically like a powerful kick. It's great for getting off the ground, but there's a glaring flaw here. You have to bring all that incredibly heavy fuel and the oxidizer with you.
What's fascinating here is the vicious cycle of rocket mass. It is a literal mathematical trap.
The rocket equation, right?
Exactly, the Tsiolkovsky rocket equation. You see, much of a rocket's launch mass isn't the payload. It's not the astronauts or the shiny rovers you care about.
What is it, mostly?
It's just the propellant required to move the propellant.
Oh, wow. So you're carrying fuel just to carry fuel.
Yes. For a long, ambitious journey to Mars, this limitation becomes a massive, potentially insurmountable bottleneck. The specific impulse, which is basically the gas mileage of a rocket for our best chemical engines, hovers around 450 seconds.
And that's the absolute limit.
Pretty much. With chemical combustion, you are strictly bound by the chemical energy stored in the molecular bonds of the fuel and the oxidizer. Once you combust them, there is a hard physical limit to how fast you can eject that exhaust out the nozzle.
So if chemical rockets are just this quick, incredibly heavy kick, how do we actually sustain speed across millions of miles of empty space?
That is where we enter the first of NASA's 2 nuclear strategies.
Right, the sprint approach.
Yeah.
Nuclear thermal propulsion, or NTP. Let's break this down. It's essentially a 3-step process, isn't it?
It is. First, you have a nuclear reactor that splits uranium atoms to create massive, massive amounts of heat.
We're talking over 2,500 Kelvin, right?
Easily. Then, step 2, you take liquid hydrogen, which is stored near absolute zero, and you pump it directly through that incredibly hot reactor core.
Which just sounds insanely violent.
It is extreme engineering. The thermal shock is mind-boggling. The liquid hydrogen flash boils instantly into a high-pressure gas.
And then step 3, that superheated gas just blasts out the nozzle at extreme velocities.
Yeah. Exactly. Because hydrogen is the lightest element in the universe, when you impart that much thermal energy into it, the molecules accelerate to phenomenal speeds. You effectively double your gas mileage compared to chemical rockets.
So this is why you call it the sprint approach.
Right. It can reduce travel times to Mars by up to 25%.
Wow.
It turns a miserable 6+ month voyage into a brisk 3 to 4 month sprint.
And I want to point out, this isn't just about impatience, it's about survival. A shorter trip means drastically less exposure to cosmic radiation for the crew.
That is the critical biological factor.
Because galactic cosmic rays, these heavy atomic nuclei traveling at near light speed, when they hit a traditional metal hull, they don't just stop.
No, they shatter. It causes spallation. It's like a shotgun blast of secondary radiation flooding the cabin. Adding thick shielding can actually make it worse because you're just giving the rays more material to smash into.
So speed is the only real shield we have.
Speed is your absolute best defense. Get out of deep space as quickly as possible.
And sprinting also widens our launch windows, right? Like, currently, Earth and Mars only align favorably every couple of years.
Every 26 months, yeah. You're locked into these slow, low-energy Hohmann transfer orbits.
But NTP gives us the sheer speed and flexibility to launch more often. And crucially, it gives us an abort option. If something goes wrong on a chemical rocket halfway there, you're out of luck.
You're riding it all the way to Mars.
But with a thermal nuclear engine, you actually have the power to hit the brakes and return to Earth if necessary.
That safety margin alone makes NTP mandatory. But sprinting requires a massive amount of energy, and liquid hydrogen is incredibly uncooperative.
Yeah, it's not dense at all, is it?
It's not even a little. To carry enough of it, you need propellant tanks the size of office buildings, which is fine for a lightweight crew capsule, but terrible for hauling heavy cargo.
So let me play devil's advocate here for a second. If we have this incredible, super fast thermal engine, why are we even bothering with a second type of engine? Isn't faster always better?
Not if you're trying to move a mountain. That brings us to the second approach. Nuclear electric propulsion, or NEP.
The marathon runner.
Precisely. Instead of using the reactor for direct heat, it generates electricity. Megawatts of continuous electrical power.
And this electricity powers an ion thruster.
Yes. It accelerates charged atoms, usually a heavy, inert gas like xenon, out of the nozzle using electromagnetic fields.
But the thrust is tiny, isn't it? I read that holding an ion thruster on Earth feels like holding a piece of paper.
It is incredibly low thrust. If chemical propulsion is a powerful kick, NEP is a persistent hand on the shoulder.
A persistent hand on the shoulder. I like that.
It's a gentle push, but it is incredibly fuel efficient, and it can run continuously for years.
It's constantly accelerating.
Exactly. And the huge advantage here is that NEP remains highly effective far away from the sun.
Right, because usually ion thrusters use giant solar panels.
But due to the inverse square law, solar energy drops off dramatically the further out you go. By the time you reach Mars, sunlight is less than half as intense as it is at Earth.
So a heavy cargo tug would need solar panels the size of football fields.
Which are fragile and heavy. A nuclear reactor entirely bypasses that. It gives you massive power in total darkness.
Okay, so how do these two distinct technologies, the sprinter and the marathon runner, actually look when applied to a real scheduled mission?
Well, this isn't just theoretical anymore.
No, it's not. This brings us to NASA's concrete plan. The Space Reactor 1, or SR-1 Freedom mission.
This is the Pathfinder.
Targeted for launch in December 2028. It is going to be the first ever nuclear-powered interplanetary spacecraft.
It's an aggressive timeline, but it's absolutely necessary.
And what's wild is its cargo. When it arrives at Mars, roughly a year after launch, SR-1 Freedom is going to deploy the Skyfall payload.
The autonomous helicopter drones.
Yeah, a whole fleet of them designed to scout the Martian surface.
Yeah.
But the aerodynamics of flying on Mars, it's a nightmare, right?
Oh, it's a brutal engineering paradox. The atmosphere is about 1% the density of Earth's, so you have to spin the rotor blades incredibly fast to generate any lift.
But the speed of sound is much lower there because it's cold and mostly carbon dioxide.
Exactly. It's around 240 meters per second. So as those rotors spin faster to catch that thin air, the tips of the blades approach the Martian speed of sound.
Which creates massive shockwaves and drag.
It's a very narrow, punishing aerodynamic envelope.
But if we connect this to the bigger picture, the true purpose of SR-1 Freedom isn't actually just to drop off these cool drones, is it?
No, not at all. If we connect this to the bigger picture, SR-1 Freedom is an uncrewed NEP mission meant to prove the bus itself.
Prove that a space-rated fission reactor can actually work.
Yes. It has to prove that nuclear energy can provide sustained, high-efficiency power in deep space. It's about creating a regulatory precedent and activating an industrial base for future nuclear fission systems.
Right, waking up the supply chain, the safety protocols, all of it.
Yeah.
Because proving this technology with robots is one thing. But how does this change the game for human astronauts?
This is where we bring everything together.
Because, let's face it, our bodies are not built for space. We talked about the bone and muscle loss, the radiation risks.
So we use the ultimate tag team strategy. We don't just use one engine, we use both.
Oh, this is the split mission architecture.
Exactly. Step 1 is the marathon. You send the heavy, vital cargo, the habitats, years of food supplies, life support machinery, huge pressurized rovers using the highly fuel-efficient nuclear electric propulsion.
Right, because it doesn't matter if a carbon fiber habitat takes 9 months or even 18 months to arrive. It doesn't get cancer.
Exactly. You use the incredible efficiency of NEP to haul all that mass slowly but surely. You pre-position everything on the Martian surface.
So it's all just waiting there, fully operational.
Yep. And once Mission Control confirms that the fully stocked base is ready, then, and only then, do you initiate step 2. You launch the human crew using nuclear thermal propulsion.
Because they aren't dragging thousands of tons of cargo, they can just punch it.
They make the crossing in a brisk 3 to 4 months, minimizing all those health risks, and they arrive at a fully prepared infrastructure.
It sounds like a perfect, flawless plan. So, what is standing in the way of a 2028 launch?
Reality, physics,
Yeah.
and bureaucracy.
Yeah. So what does this all mean? We've known the physics of nuclear propulsion since the Cold War. The physics are sound. Why are we only targeting this now? And why is December 2028 considered incredibly ambitious?
Well, the push really started aggressively when Jared Isaacman took over as the agency's chief back in December 2025.
Right, he made this his absolute priority.
She fundamentally believes this technology will truly unlock humankind's ability to explore among the stars. But enthusiasm doesn't rewrite the laws of thermodynamics.
Oh, definitely doesn't.
The monumental engineering and regulatory hurdles are sobering. An NEP spacecraft requires flawless integration of a reactor, massive shielding, heat management, power conversion, radiators, electric thrusters.
Just an unbelievable amount of tech.
And fault tolerance. Because in space, convection doesn't exist. You have to reject the massive waste heat from the reactor as infrared radiation.
Wait, so the reactor heat could literally melt the other components?
Oh, easily. If the heat management system fails, that thermal energy will travel right through the chassis and physically melt the avionics and the payload.
That is terrifying.
And you have the radiation environment created by your own power source. You need rad-hardened microchips that won't suffer from single-event upsets, where a rogue neutron literally flips a 0 to a 1 and crashes your flight computer.
So you need computers that can autonomously heal themselves, because the communication light delay to Mars means Earth can't help in real time.
Exactly. And look at the historical track record. Making this safe, affordable, and able to pass regulatory safety standards is brutal.
Yeah, I mean, the U.S. has only ever launched one fission reactor into orbit, right?
The SNAP-10A. Way back in 1965.
And it only ran for, what, 43 days?
43 days before a voltage regulator failed and shut the whole thing down. Since then, we've only used RTGS radioisotope thermoelectric generators on things like the Curiosity rover.
But those just use passive K-heat. They don't split atoms.
Right. They produce a tiny trickle of power. To jump from that to a no, it's about breaking down the barriers of deep space entirely.
Think about it. If we successfully tamed the power of a nuclear reactor to push us across the void, turning an expedition of pure survival into a routine 3-month commute, where does the boundary of human territory actually stop?
If Mars is just 3 months away, the outer solar system opens up.
Exactly. What becomes our next impossible destination? Could we use this to haul submarines to Jupiter's moon Europa? Or set up atmospheric processing plants on Titan?
The asteroid belt becomes a viable logistical hub instead of just a deep space anomaly.
The systems we're forcing into existence for this 2028 window are the exact same engines that will turn us into a true deep space civilization. So thank you for joining us on this exploration of the future of space travel. Keep your eyes on the stars, and definitely keep your eyes on the launch pads in December 2028.